In the modern era of space exploration, few technological creations symbolize endurance and engineering refinement as clearly as the Orlan-MKS spacesuit. Developed by Russia's Zvezda research and production enterprise, this latest generation of Orlan suits continues a design legacy that has protected cosmonauts for more than 5 decades. The Orlan-MKS is not merely an upgrade, it represents a complete modernization intended to keep Russian extravehicular activity capability reliable and competitive through the middle of the 20th century. The Orlan lineage began in the early 1970s when Soviet engineers sought a durable, semi-rigid spacesuit for extended work outside orbiting stations such as Salyut and Mir. The term Orlan means sea eagle, symbolizing both strength and precision. The original Orlan-D introduced a unique rear-entry hatch design, allowing cosmonauts to enter and seal the suit quickly without assistance, a feature that has defined every successor, including the MKS version. By the time the Orlan-MKS appeared in the 2010s, its predecessors, models D, DM, DMA, and MK, had collectively supported hundreds of spacewalks. Yet the demands of modern missions aboard the International Space Station required improved materials, digital life support monitoring, and extended service intervals. The Orlan-MKS integrates those enhancements while retaining proven mechanical simplicity. The suit's structure combines a rigid fiberglass resin torso with flexible limb assemblies. This semi-rigid configuration allows the pressure envelope to hold steady at roughly 400 hectopascals, equal to 5.8 pounds per square inch, while maintaining enough mobility for tool manipulation and station maintenance tasks. The inner bladder is a multi-layer hermetic film, while the outer shell consists of heat-resistant and radiation-resistant synthetic fibers, including aramid, polyester, and Teflon-coated fabrics. An important hallmark of the Orlan-MKS is its power-assisted life support backpack, known as the BK3 system. Within this unit are oxygen cylinders, carbon dioxide scrubbers, thermal control pumps, and communications electronics. The entire assembly operates autonomously for up to 7 hours of extravehicular work, with an additional 30 minutes of emergency reserve. Weight on Earth is approximately 110 kilograms, equal to 242 pounds, but in microgravity, mass rather than weight governs maneuvering dynamics. The Orlan-MKS introduced a digital telemetry interface connecting the suit's sensors with onboard computers in the International Space Station. This allows mission control to monitor oxygen pressure, temperature, and power status in real time. Earlier analog versions required manual reporting by voice, which could distract crew members during complex repairs or scientific tasks. By automating diagnostics, the MKS improves both safety and mission efficiency. Thermal regulation is handled by a closed-loop, liquid cooling garment worn beneath the main suit. Chilled water circulates through narrow tubes that absorb body heat and transfer it to a sublimator plate located in the backpack. As ice sublimates directly into space, excess heat is removed, keeping the astronaut's core temperature stable between 20 and 25 degrees Celsius, equal to 68 to 77 degrees Fahrenheit. The automatic system adjusts flow based on body activity, reducing fatigue during prolonged extravehicular activity. Illumination and visibility have also been refined. The Orlan-MKS helmet integrates high-efficiency light-emitting diode lamps and a newly designed visor with improved ultraviolet shielding. Optical coatings minimize glare from the sun while maintaining clear peripheral vision for work around reflective surfaces of solar panels and station modules. The helmet also houses dual high-definition cameras that transmit live imagery to ground controllers and record mission footage for analysis. Communication reliability represents another leap forward. The MKS system employs a redundant radio network, allowing both short-range and long-range data transfer to the spacecraft. This dual-channel setup ensures uninterrupted voice contact, even if one transmitter experiences interference or power fluctuation. The internal microphone and earpiece are built into the helmet liner, providing clear audio despite the constant hum of pumps and fans within the suit. Ergonomic adjustments have been redesigned for comfort and adaptability. Each suit can be adjusted to fit astronauts between 165 and 190 centimeters tall, equal to 5 feet 5 inches to 6 feet 3 inches. Internal harnesses, arm extensions, and glove fittings can be swapped or fine-tuned aboard the station. These modifications reduce the number of suit sizes required and simplify logistics for long-term missions. Electrical power is supplied by lithium-ion battery packs positioned within the life support backpack. The battery modules are quick-change units rated for more than 500 charge cycles, ensuring operational readiness between maintenance intervals. Charging occurs through onboard interfaces while the suit is docked in its airlock cradle. For safety, thermal sensors automatically disconnect power if abnormal heat buildup is detected. During assembly and testing, every Orlan-MKS undergoes pressurization, leak, and mobility checks inside vacuum chambers at Zvezda's facility near Moscow. Each suit is designed for up to 20 reusable cycles before major overhaul. Components such as gloves, visors, and seals are typically replaced after 5 to 10 missions, depending on wear. These maintenance protocols have proven critical for sustaining reliability on long-duration expeditions. By combining proven mechanical design with 21st-century materials and electronics, the Orlan-MKS extends the operational lifespan of the Russian extravehicular activity program well beyond 2030. Engineers estimate that future variants could serve aboard next-generation orbital platforms or even lunar missions, provided suitable environmental modifications are introduced. Such adaptability demonstrates the enduring ingenuity of the Orlan design philosophy. Although the Orlan family of spacesuits has earned a reputation for reliability, every extravehicular activity suit reflects a balance of engineering compromises. Designers must reconcile flexibility, safety, and operational simplicity with the extreme environmental requirements of space. The Orlan's semi-rigid torso and articulated limbs embody this compromise, giving astronauts both protection and mobility. One of the defining ergonomic strengths of the Orlan series is its rear entry design. The entire back of the suit opens as a hinged hatch, allowing the astronaut to step in and close it without external assistance. The entire process takes roughly 5 minutes, compared with 20 or more for certain American models. This feature is invaluable when time and airlock resources are limited. The suit's design also emphasizes redundancy. Core systems such as oxygen circulation, communications, and thermal control each have independent backups. Even if one component fails, the astronaut can safely return to the airlock. This philosophy of layered protection has guided Russian spacesuit design since the earliest Voskhod and Sokol suits. Long-term serviceability was a major goal during MKS development. Unlike the earlier Orlan-MK, which required partial disassembly and Earth-based refurbishment, the MKS can undergo most repairs in orbit. Its modular life support pack, electronic control panels, and connectors are designed for quick replacement using onboard tools. This approach saves time, reduces cost, and extends the suit's operational life to more than 10 years. Comfort and fatigue management are equally important. The Orlan-MKS integrates new materials inside the pressure bladder that reduce friction and chafing during long spacewalks. Improved bearings in shoulder and elbow joints make repetitive motion less tiring. Gloves have enhanced fingertip tactility for delicate instrument handling, addressing one of the long-standing complaints of earlier designs. Safety during extravehicular work depends heavily on reliability of the life support system. The Orlan-MKS incorporates automatic oxygen regulation, allowing the internal pressure to remain constant even when the astronaut changes orientation or moves between shaded and sunlit areas where temperature differences exceed 100 degrees Celsius, equal to 180 degrees Fahrenheit. Sensors track oxygen partial pressure, humidity, and fan speed in real time. Temperature extremes present one of the most severe hazards. When working in direct sunlight, the outer surface can reach plus 120 degrees Celsius, equal to 248 degrees Fahrenheit, while shaded areas plunge below minus 150 degrees Celsius, equal to minus 238 degrees Fahrenheit. The Orlan's multi-layer insulation, reflective visor coatings, and cooling garment maintain internal stability despite this enormous gradient. Operational experience aboard the International Space Station has validated these systems. Russian cosmonauts have used the MKS for numerous maintenance tasks, including solar array adjustments, scientific experiment installation, and structural inspections. Each successful mission confirms the system's durability and demonstrates how incremental upgrades have extended its usefulness. Communication between the Orlan-MKS and the International Space Station follows a dual-channel approach. The primary link carries voice and suit telemetry data, while the secondary link transmits video from helmet cameras. Mission controllers in Moscow can view the astronaut's field of vision and offer guidance in real time, dramatically improving coordination between ground specialists and crew members in orbit. Lighting conditions outside the station can vary dramatically, especially when crossing the boundary between day and night every 45 minutes. The integrated high-intensity light-emitting diode lamps in the helmet automatically adjust brightness, ensuring that tools, tethers, and work surfaces remain visible in total darkness or harsh glare. This automation reduces mental load on the astronaut, who must already manage complex procedures and safety checks. The internal monitoring console of the Orlan-MKS provides real-time readouts of oxygen pressure, battery charge, temperature, and system alarms. The compact digital display replaces the mechanical gauges of older Orlan models. Audible alerts notify the astronaut if any parameter drifts beyond safety margins, ensuring immediate awareness even during visually demanding tasks. Maintenance aboard the station includes regular leak checks, battery cycling, and filter replacements. These are conducted inside the Purs and Poisk modules, which act as both airlocks and suit servicing facilities. Specialized racks hold the suits upright while technicians refill oxygen cylinders, clean cooling garments, and inspect seals. The self-contained nature of the MKS simplifies this routine compared to the more component-intensive American system. Over time, feedback from cosmonauts has led to small yet important improvements. The placement of tether hooks, tool attachment points, and camera angles has been refined based on real experience. Even minor enhancements, like reoriented wrist mirrors for checking rear connections, can reduce workload and improve safety. Physiological monitoring plays an increasing role in extravehicular activity safety. The Orlan-MKS can interface with medical sensors embedded in the cooling garment, tracking heart rate and body temperature. Data from these sensors helps mission control evaluate stress and fatigue levels, allowing for timely recommendations such as rest breaks or early return to the airlock if conditions warrant. Russian engineers have also studied ways to adapt the MKS for lunar and deep space operations. Potential modifications include dust-resistant joints, thicker radiation shielding, and more powerful cooling systems capable of handling lower gravity environments where convective heat transfer is negligible. These studies demonstrate how the Orlan architecture can serve as a foundation for future exploration suits. From an operational standpoint, the Orlan's modular and autonomous nature has proven cost-effective. Unlike the American Extravehicular Mobility Unit, which is built around a life support system integrated into the primary suit body, the Orlan's backpack can be detached and serviced separately. This design lowers maintenance complexity and allows one station to support multiple suits with shared components. The American Extravehicular Mobility Unit, often called the EMU, remains the United States' primary spacewalk suit. Developed by the National Aeronautics and Space Administration in the early 1980s, it has supported hundreds of spacewalks aboard the Space Shuttle, and the International Space Station. Although highly capable, its operational concept differs fundamentally from the Russian Orlan series. The Extravehicular Mobility Unit is a modular suit that requires assembly from separate components before each spacewalk. The hard upper torso, lower torso, arms, gloves, and life support system are joined manually and then checked for leaks. Astronauts need assistance from teammates and technicians to don it, a process that can take 30 minutes or more. In contrast, the Orlan's one-piece rear entry design allows a single cosmonaut to suit up independently within 5 minutes. Another difference lies in service philosophy. The Extravehicular Mobility Unit requires periodic return to Earth for refurbishment and calibration, whereas the Orlan-MKS is intended to remain on orbit for up to 6 years without full overhaul. Its modular electronics and replaceable life support components enable long-term maintenance in space, a crucial advantage when logistics are limited. Both suits operate at similar internal pressures. The Extravehicular Mobility Unit maintains approximately 29.6 kilopascals, equal to 4.3 pounds per square inch, while the Orlan-MKS operates around 40 kilopascals, equal to 5.8 pounds per square inch. These differences influence mobility and pre-breathing procedures before an extravehicular activity. The slightly higher pressure of the Orlan reduces decompression risk but requires a bit more effort for joint movement. In terms of suit mass, both are roughly comparable. The Extravehicular Mobility Unit weighs around 113 kilograms, equal to 249 pounds, while the Orlan-MKS is close to 110 kilograms, equal to 242 pounds, depending on configuration. Despite similar mass, the Orlan's self-contained structure makes handling simpler during donning and maintenance. For power supply, the Orlan-MKS relies on rechargeable lithium-ion batteries capable of supporting up to 9 hours of extravehicular activity, while the American suit's batteries generally sustain 7 to 8 hours. Both systems incorporate redundancy to ensure life support stability during emergencies. The communication setups also differ. The Extravehicular Mobility Unit transmits through the United States Tracking and Data Relay Satellite System, while the Orlan uses direct relay via the International Space Station's Russian segment and ground stations operated by Roscosmos. Each system integrates voice, telemetry, and video, though their protocols and encryption standards remain distinct. When comparing mobility, astronauts often note that the Extravehicular Mobility Unit offers greater shoulder freedom but requires more assistance for fitting. The Orlan's slightly stiffer arms limit extreme reach but improve reliability and structural integrity. Over decades of parallel evolution, both suits have achieved an effective balance suited to their respective operational doctrines. As Russia plans its next-generation space projects, including the proposed ROS, or Russian Orbital Service Station, the Orlan-MKS provides a proven baseline for future extravehicular systems. Engineers envision lighter, more flexible versions, incorporating advanced polymer composites, enhanced radiation shielding, and digital heads-up displays within the helmet visor. Further developments may include hybrid vision systems capable of overlaying telemetry, navigation, and tool instructions directly onto the visor through augmented reality. This would minimize reliance on printed checklists and manual coordination with mission control. The goal is to streamline extravehicular operations and increase autonomy for crews stationed farther from Earth. Adaptation for lunar and planetary environments remains an important challenge. The Orlan-MKS was optimized for microgravity operations in low Earth orbit, not for dusty surfaces or gravity-dependent tasks. Future versions must accommodate lunar regolith resistance, radiation exposure, and more efficient heat management in vacuum environments where solar illumination is harsher. Russian research institutions, including NPP Zvezda and the Institute of Biomedical Problems, are already experimenting with reinforced bearings, dust seals, and flexible joints designed to resist abrasion. These upgrades could make the suit suitable for lunar orbit or short-surface sorties associated with the Russian-Chinese International Lunar Research Station project. The Orlan-MKS's ability to remain operational for up to 6 years without complete return to Earth underlines a significant logistical advantage. When deep space missions to Mars or long-duration lunar stays become routine, such long service life will be essential. It demonstrates a design philosophy prioritizing durability and field serviceability over frequent replacement. Material sourcing poses new technical challenges under current geopolitical conditions. Reports suggest that certain specialized polymers used in the Orlan-MKS's polyurethane outer shell are now being localized to ensure complete domestic production capability. This effort aligns with Russia's broader goal of achieving technological independence in high-performance materials. Meanwhile, the Orlan-MKS continues daily service aboard the International Space Station. As of 2025, suits numbered 4, 5, and 6 remain active on the Russian segment, supporting routine maintenance and research operations. New units are periodically delivered aboard Progress spacecraft to replace aging ones, ensuring uninterrupted extravehicular readiness. The continued use of the Orlan-MKS demonstrates the enduring efficiency of its evolutionary design approach. Rather than discarding proven concepts, Russian engineers have progressively refined them over 4 decades, building reliability layer by layer. Each new model, D, DM, DMA, MK, and now MKS, represents both technological progress and continuity of experience. As future missions extend to lunar orbit, deep space, and possibly Mars, lessons learned from the Orlan-MKS will guide development of new generation suits with integrated robotic support, flexible exoskeletal assistance, and real-time telemetry overlays. These innovations will ensure cosmonauts remain protected, agile, and efficient even in the harshest extraterrestrial environments. In conclusion, the Orlan-MKS stands as the most advanced evolution of Russia's extravehicular suit heritage. Combining decades of proven engineering with modern materials and automation, it continues to define human presence outside spacecraft. Its ruggedness, self-sufficiency, and ease of use make it one of the most capable extravehicular systems in service today. While its operational domain remains orbital rather than planetary, the Orlan-MKS has set the standard for future designs that will one day enable humanity's sustained activity beyond Earth orbit. Whether servicing satellites, assembling space habitats, or supporting lunar bases, its design philosophy, simplicity, durability, and autonomy will continue to shape the future of human space exploration. The Orlan-MKS is more than a piece of technology. It is the culmination of over 40 years of engineering refinement, symbolizing the enduring human pursuit of safety and capability in the vast and unforgiving realm of space. If you think the video was informative, please like, subscribe, and share. Please also take membership of the channel to encourage us